Hey, Connor Wander here with the Straight from Scientist podcast. This is an episode that is completely out of our wheelhouse. I know we're normally life science, health related, medicine related kind of content, but I had the opportunity to join last minute a 3-minute thesis competition, which is essentially just elevator pitches of whatever graduate students are working on around the UNC campus. And one of the people that really stood out to me was Mugdha Polimera. She is a scientist, yes, of course, studying astrophysics in UNC Chapel Hill, and she's actually uniquely working on supermassive black holes in dwarf galaxies. And I know that may not make sense right now, but Mugdha explains it beautifully in the episode. It was a real mind blower for me, especially I know like very little about astrophysics and kind of how the universe works. I've been studying cells and focusing on very small things, so it was really, really great to get that insight and kind of broaden my wheelhouse as well. I think you'll enjoy it absolutely. This was another video episode. Again, we are on YouTube right now, so if you're watching this, of course you know that. If you're just listening, the YouTube will just kind of help you. We make a few visual aids in the podcast, and I am working on maybe ways we can help put graphics in the future. So let me know what you think about the whole video setup, and subscribe to our YouTube channel. That's Straight from a Scientist on YouTube as well. Thanks all for listening. Of course, we love you can review us on iTunes, Stitcher. We're on Spotify. We're on all those platforms right now. If there's any platforms you want us to get on, let me know, and we can make that happen. So enjoy, y'all. Welcome everyone, Straight from Scientist podcast here. I'm Connor Wander here with Mugdha Polimera.
Yes, that is me.
And she is a graduate student here in astronomy.
Yes. I mean, I think at this point it's the same, but what we like to call it is astrophysics. And I personally do astrostatistics as well. So it's a little spin on combining statistics with astrophysics.
So me and Mugdha connected from a 3-minute thesis talk. There's a ton of great science communication resources, and for only 3 minutes, so you can go check some of those videos out on the 3minutethesis.com website. But first off, thanks Mugdha for joining us here.
Oh, thank you for having me. This is awesome.
Yeah, I was really interested with your research when you presented. Just 3 minutes, of course, caught my eye. You research supermassive black holes, but in dwarf galaxies.
Correct.
So could you intro that for us, please?
Yeah, sure. So the way I like to, introduce it to people, especially because there's a little wordplay there, is what I like to do is find massive black holes in little galaxies. And, I think, obviously, to everybody, what are black holes? This is really interesting. This is this really cool thing that... honestly, we don't have the answer to, but the reason why this caught my eye is because I was researching black holes before, even before I got into this project. But so a little bit of fun facts. So almost all galaxies, like our Milky Way, the one that we live in currently, have a supermassive black hole in the center. They might not all be, contrary to popular belief. I'm sorry if I'm bursting people's bubbles, but black holes don't just go around eating things whenever and wherever. It's actually incredibly hard to get something to be close enough to a black hole for the black hole to actually start eating it.
That's good news, I guess.
Yeah, it's good news. A lot of people are very disappointed by that. Like, no, you just ruined my bubble that black holes are these cool things that eat things. I'm like, well, they do, but it's just hard to feed them. So all giant galaxies, it's an actual technical term, I'm not making this up, like our Milky Way, have a supermassive black hole in the center. But scientists have found that almost 100% of these have these black holes in the center. But our current most widely accepted model of how galaxies evolve through time and how, the cosmos has evolved through time is just, it's very simple. It's like smaller things come together to make bigger things. And I think that's just generally how, things in the world work. And so, they were like, okay, the galaxy must do the same thing. So somehow, even though people believe that's true, there was never actually any evidence until, the past 20 years that small galaxies, which are supposed to be the building blocks for these bigger, larger, massive galaxies, there were never actually evidence these small galaxies had black holes, which didn't make any sense. Right. Because then you're like, well, if you say that these small things come together to make the big thing, and you say that the big thing definitely has a black hole, then where did it come from? And it was just this really weird paradox, which people were like, oh, these dwarfs are boring, they don't have anything. Turns out they're not.
Not interesting.
So so that was the whole context, and now this field is booming. There's I'm not sure if people are familiar with the archive. It's I don't know if it's only physicists who use this, but it's just basically this online webpage that before things even get published, because there's a delay by the time papers get accepted and then they are in print. So every day people will submit stuff to this archive as soon as they get accepted. So there's like this fresh slew of papers that are just coming out every single day. And every single day you'll find a paper about this topic. So it's like, it's a
hot topic right now.
It is. And it's very exciting, all kinds of things that people are finding. So, so given that, in the past couple decades that people have actually found evidence for this, me and my research group are actually taking a different spin on the same topic, as all scientists do. And we're very excited about this science.
Excellent. I think we should probably step back a little bit and talk briefly for those who don't necessarily know what black holes are. You might have seen them in the media. I know there was that image that was produced that did the rounds, and it's fascinating. And then I think Interstellar was a movie that probably popularized the event horizon and all of that. But to my understanding, correct me if I'm wrong, black holes are just these massive gravities. We like to think of them as eating everything, but at the very least, they're kind of attracting everything around them, no?
Right. Yeah, you're absolutely correct. Yeah. So the thing is, how they're formed is a question yet to be answered, which we, ultimately all of us hope that we can do it in some part. But what they are is they're just extremely compact objects. So, gravity scaled with mass. So the bigger something is, the more gravitational effect that it has. So these black holes have the mass of a million or 1 billion suns. But that's a lot. Like the sun is extremely massive. It's I don't even know how to say this in real numbers. I don't think it's 10 to the 30 kilograms. And if that means anything to anybody, 10 to the 10 is a billion. So this is it's not 3 billion, it's just a billion raised to a billion. Yeah, it's extremely big. 10 to the 30 is a lot.
These are numbers that we as humans can't even
comprehend. And that's the thing that I know, the universe is such big numbers and you just don't really understand. Just for scale, if I may. So somebody did this math to actually make people understand. They're like,
1 million seconds is 11 days, but 1 billion seconds is 31 years.
Yeah, I know that everyone uses millions and billions interchangeably, but they're really not. 31 days is very different from 11 years. So that's just, that's just for scale. So, so it's basically something with the mass of a million or 10 million or 100 million suns, but the volume that it occupies is definitely less than the sun. So it's probably half the size of the sun. So it's can you imagine compressing 1 million suns into a pocket which is half the size of the sun? So that's why it's extremely, extremely dense, and that's why its gravitational energy is so strong. And essentially what it does is it warps space-time. So it's just like, if you're trying to go straight, if you're close to a black hole, you will just like space itself is bent because of the fact that anything that goes close to the black hole will just get sucked right into it. That's because it cannot escape the attraction that the black hole has on it.
And not even light, right? That's why they call it.
Yes, not
holes,
even light. That's why it's the black hole, because
dark spots in space if you're just viewing through a light telescope.
Yeah, I mean, that's the reason why optical telescopes, or things that work in the same wavelengths that our eyes can see, like the rainbow colors, essentially, can never see a black hole because there's nothing to see. Like you can, what we see through a telescope is the light that is emitted by these objects, but these black holes, by essence, just absorb everything, so they're never radiating anything, hence we can't see them. So it was like if a person was not reflecting light, you just wouldn't see them. They would be transparent.
So that's the only reason I can see you. And then, for example, your coffee mug, the microphone are absorbing more light and they're reflecting. It's dark. A black hole is, there's I think a paint called Vanta Black, which is like super, super dark and it makes things almost disappear. So that's kind of how I imagine a black hole, except actually just completely.
It's just nothing leaves it.
So that's how they work. They seem terrifying. I'm glad you said that they're not actively eating everything. Is that just because the objects don't come close enough?
Right. So there's usually this region around a black hole that clears out just by effect of this black hole being there, and then this extremely strong gravity source in the center, if you will. But it's also just an effect of space, like there's a lot of empty space. There's just, things between planets, there's just so much empty space so one, the density of just anything in space is very low, and then everything in space, as everything even on Earth, everything wants to sit. All of us are lazy. Like all of us want to be in a position with expending the least amount of energy possible, and that's exactly how things work in space. So they just they don't want to be in this region where it's extremely unstable. Right. And so it's just really hard to get something across there. So if something comes close by, if it's beyond a certain distance from the black hole, it just get deflected, and then it will probably speed up like a comet around the sun.
Slingshot effect.
Yes, exactly. It slingshots back. So it's like you rarely ever see like comets going into the sun, right? Like they always orbit back and then they get slingshotted back, and then like the Halley's Comet does it every 94 years or so. So so that's exactly what even stars and stuff would do around a black hole, that they would it just would be incredibly hard to get something that close to such a massive object. However, it does happen, and when something breaks through that distance where it's now impossible to get out, then you start accreting material onto the black hole, and that's how my research group actually studies black holes. So we don't study them when they're in their inactive or dormant state. We actually study active black holes.
The interesting ones.
I like to think that they're interesting.
Sure, everyone's a little biased towards their own research, and rightly so, right? So I guess I have a couple questions on that. Sure. Let's say Halley's Comet's coming around every 94 years. Could be wrong about that, but it's making that pass. Eventually, does it get close enough to the sun where it can't escape? I mean, unless its trajectory were altered in other way, maybe it's millions of years from now. Is it assumed that eventually it'll go in, or is it in such a stable orbit? Maybe Halley's Comet is a bad example, but other objects, are they so stable in their orbit that they will never get close enough?
I would like to say that they're stable definitely on human life scales.
Sure, yeah.
I honestly have no intuition for within a million years, like if a comet, but also realize that within a million years the sun's not going to be the same. True. So the effect of its gravity is going to change. So
an active black hole.
An active black hole will definitely grow and evolve. If things are getting pushed into it, then that energy must be converted to mass, because you can destroy or create energy. It has to all be conserved. So yeah, I mean, I know a lot of that's how scientists in our Milky Way, I know this is hard to imagine, but it's actually harder to study about our own galaxy than other galaxies. It's easier. It's like looking at a pizza face on versus being like a pepperoni on the pizza and trying to figure out what it's in the rest of the pizza. It's really hard because like you have so much stuff to get through.
That's a great visual. Yeah.
Yeah. So the reason people actually found a supermassive black hole in the center of our galaxy is because there were these few stars in the direction of the galactic center that would just have really weird eccentric orbits. And same thing, like similar to like comet orbits, where they would like speed up like ridiculously high speeds and then really, really slow down and then do the exact same thing, but extremely odd orbits. Like they were almost they were disturbed somehow from the plane of the rest of the galaxy, and then they're just doing their own thing. And they that's how they did a lot of complicated math and figured out that it must be the presence of this really massive black hole that's messing with these. So so to answer your question of if they will eventually sink in, I assume that they will, because
given enough time. Sure.
Yeah, because like actually dynamical friction in space is a real thing. Everything changes, but also I know for a fact that in the timescales that would happen, a lot about the system itself changes. So then if it's just friction that's eventually gonna reel this thing in, or if it's the fact that the whole system has changed, like somehow the black hole has gotten massive or something like that. So yeah, I don't know which comes first.
Eventually, yeah. And of course this is on timescales that make no sense. But I guess that brings me to the real research question you're looking at, is why do these dwarf galaxies harbor black holes? Or what is, like, what keeps you up at night, I guess, and what drives you in the lab?
Yeah, I mean, well, so I guess it's one, it was this whole discrepancy that they're like, everyone's saying we have almost 100% of these big galaxies have these supermassive black holes, like I just said. And so then you're like, where are these dwarfs? Because these tiny dwarf galaxies are also not just small, but they're young. They have like a lot of fresh gas coming straight from the cosmos, like not stuff that's been reprocessed, but just pristine gas from the cosmos. So they're actually like the closest in the present day universe to galaxies were in the past, when the universe as a whole was very young. So when galaxies were first born, they were probably most like the dwarfs that we see that are close by. So again, one more thing, which I think this was objectively the coolest thing that I realized when I was studying astronomy. As you look further back into space, you're looking further back in time. So, and that is just so cool, because it's just like, the universe is a giant time machine, and this is crazy. So, yeah, a little bit, if someone hasn't heard that before, it's just because light travels at the speed of light. So,
a speed limit.
Yes, it's like a speed limit. So because these distances, and on Earth you never see that because the distances are never big enough to actually feel the effect of light. Also, if you didn't know that from the sun to the Earth, light takes about 7 to 8 minutes to get here. So that's how far the Earth is from the sun, and that's not a huge distance at all. So in space, obviously things are going to take a lot longer to reach you. So so what you're seeing of a galaxy that is far away is probably what it looked like a few years ago or a million years ago, depending on the distance that you're looking at. So so when we find these galaxies that are really, really far away from us, we know that what we're seeing right now is what they were like a few million billion years ago. And but it's hard to actually study them the way that we can study things that are close to us, because just because our optics and our instrumentation, we have limitations to that, and they're so far away, so there's only certain things that you can actually study about them, versus things that are close to us, with the amazing advancements in telescope and software and everything, we can actually learn so much more about them. In just like, we don't just see them and study the pictures, but we also take spectra, which is effectively, you put a much fancy $1 billion version of a prism in front of the telescope and allow the light to spread into its own rainbow. And the rainbow that the galaxy makes will actually tell you what it's made of. And there's a lot more that you can study about its composition, its chemical composition, and its age, the history that it may have gone through, and the kinds of processes that are going on in the galaxy. There's a lot that you can uncover from that. And so as I was saying, that these dwarf galaxies that are close to us are the closest analogs we have to the almost all galaxies that were present in the past. So it just makes a really good playground to actually see how these black holes were formed, and how they actually grow and evolve with the galaxy, because they do. They actually, also, as the galaxy is growing and merging with other galaxies, and that's a pretty common phenomenon. Galaxies, come together, they merge into these extremely beautiful shows. If you actually look at these simulation videos or pictures, they look gorgeous when they're merging. But the black holes merge too, and that's how they grow and evolve with the galaxy. So so that's kind of the thing, is that, okay, where are these coming from? Where are these supermassive black holes coming from? And also, the other thing is that, so people have models. Well, it's really hard to be like, oh, this is the actual mechanism from which a black hole is formed. Because, well, one, you can't see it, and also, if you could see it, it's probably so far like in the past, or so far in distance from us, that it's just extremely hard to see. And I don't think we would recognize if we saw a black hole forming, because it would just, I don't think we have any kind of resolution. So
need more and better telescopes and other tools. But...
black holes forming, I don't know.
And how long would it take? Do we necessarily have estimates on that? Like, is there an actual window, or is it just, because I know black holes can form if two stars merge sometimes.
Yeah, so I mean, there is so again, with stars, we've all heard about supernovae, at least in a song or something, if not in actual scientific context. But supernovae actually happen quite simply when stars die, when they've reached the end of their lifetime, and they either become, and the remnant of the star is either a white dwarf or a neutron star, which again are really compact structures. They're not fusing anything anymore. They're just dead stars. They're not doing their nuclear reaction like all other stars do. So, and for white dwarfs is a very nice limit that was found by Mr. Chandrasekhar, and it's called the Chandrasekhar limit after him. And for neutron stars, is a similar limit in how big a neutron star can be. And the hypothesis is that after that mass is reached, if any more matter is being dumped onto this neutron star, it has to collapse into a black hole, because there's just simply no way that it can be stable. There's no way determined by statistical mechanics or quantum physics where it actually becomes a stable structure. Mm-hmm. So the theory is that these extremely massive stars will collapse into a black hole at the end of their life, but we've never actually seen that.
Yeah. And a watch pot never boils, so sitting around watching
right.
stars.
Yeah. So okay. So yeah, and so scientists got crafty, and they were like, okay, well, if we also wouldn't even know what to expect to observe, right? Like if you're just sitting and watching, well, if you don't have any clue of what's going to happen, then you're just like, well, what am I looking for? Right. Which happens a lot. So what they did is like they ran simulations, and the two, I guess, competing methods of how black holes are formed. There's one is this: either when a really really massive star dies and collapses into this well, they call small black holes, which are about 100 to 1,000 times the mass of the sun, so not super big. Yeah, not that big. Or the other one is called a direct collapse method, where it's just this really dense cloud of gas somehow collapses and becomes a black hole. It's just that one method is easier than the other to form. So this is why people went on this hunt for black holes in dwarf galaxies. It's one of the reasons is that if we can find the number of black holes that are in dwarfs, it may seem very simple logic, but I think it works, is that if we find a very high percentage of this, that means the most dominant form of black hole production is the easier method. If there's a very low percentage of this, it should be the harder method,
right?
Which kind of makes sense, but yeah. So this is the reason why they went on. We were just like, let's just count them up. Except that, you know, as with everything in science, it's really really hard to do. So that's one of the leading questions that you know that this science will hopefully be able to answer a little better. But also my entire research group's focus is galaxy evolution. So we are more interested in like what I was talking about earlier, is like how are these black holes in these small young galaxies actually affected by their environment of the galaxy itself, because they're small, young, they're you know, they're being shoved with all this cosmic pure gas. So it's like, how is that affecting the black hole, and how does that actually grow into a bigger black hole, and what effect does that have on the galaxy? And galaxies normally live in groups or clusters, so like how does it actually affect the whole environment around it? So that's the part that we are more interested in. But yeah, it's fun that as a side effect of all of that, we'll actually be able to get how common, how frequent are these black holes in these dwarf galaxies, which can won't answer the question of how they're formed, but it can help put at least a constraint that now people who do the simulations can be like, okay, this is what's observed. Let's trace that back and see what happens to the formation. I hope that wasn't too much.
No, it makes sense. So you're saying while your research group's main focus is essentially just studying these young galaxies, or like their seed black holes, figuring out all those mechanisms can really, you can let other groups know, hey, this might be a possible way that black holes form. Don't know that.
Yeah, it's just, you know, like because that's the thing, you know, everyone's like, oh, there's this discrepancy, and like just knowing the true frequency in the present day universe will, like, it's like a constraint that you put at the end of your simulation. Be like, you can run all of this simulation as long as you make X number in the present day universe. Except that X number is not known until now. So we're hoping that in the process of learning how these, you know, galaxies evolve, that we can find that number and, you know, give it to the theorists and be like, okay, now can you tell us something a little more promising about how these guys are formed?
Yeah, so astrophysics have all these levels, as we do in life science, right? So you have the drawing board people and people running calculations and simulations. You said you do a bit of statistics yourself, so you may have your hand, I would imagine. Then there's observational.
Right.
Do you collaborate frequently? Or
of course. As you know, like any science does not actually progress without collaboration. So yeah, I'm very lucky to have co-advisors, one of whom is at UNC, and she's the PI of this great survey, which is a really great playground for a lot of different kind of galaxy evolution studies. And her name is Sheila Kanapan, and we do observational sciences here. We actually use the telescope SOAR. That it's UNC's telescope. It's UNC partner with other universities, but we have a fair share of blood, sweat, and tears into that telescope. And I also have a co-advisor from Elon University. His name is Chris Richardson, and he does simulations and theoretical stuff. So I'm actually in a really, really lucky position to be co-advised by two complementary advisors, and we also collaborate with other theorists and other observational astronomy people. So it's been great, and we have the whole spectrum. I dabble mostly in observational. I try to understand the theory because and that's the reason why I said astrophysics. Because there's a lot of people, you'd be surprised that people think that astronomy doesn't involve physics or math. Like, that is just
they're probably thinking of astrology.
Oh my god, I get that so much. We
won't go down there.
It's terrible.
Not scientific. We'll leave it at that.
Because I think the difference is because in the past, astronomy was just like basically a cartographer of the sky. It was just people who were mapping out what stars were where, and that was mostly for navigational purposes, or it led to a whole other slew of things. But that's what astronomy was, and then astrophysics was left to people who were actually trying to understand the physics of celestial objects, right? Except that in today's world, you can't just do astronomy. Like, astronomy, if you're trying to publish a paper and make advances in science, you can't just be like, hey, I found something. You have to understand it in context and be like, okay, this is what this means, and you have to put this in this astrological context, astronomical context. I did it. And that's the reason why it's so important to have people understand that it's great. It's really important, obviously. Like, for me personally, it's like the physics is interesting. The all the astrophysical, like the celestial stuff, it gives me this sense of awe and this sense of like drive. I think I'm like, this is so interesting. I want to figure it out. But at the end of the day, what we realize that, oh, we're doing physics, and it's this really weird thing where I don't know how people ever got this intuition that astronomers don't do physics, but I'm like, kind of do. It's kind of impossible to do all of this without any kind of physics, but okay. And out of all of this, it's also just the survey that I work on is very, very primed for statistical studies, because just of its design, and so we do a lot of detailed statistics, and it's like, data science is a very broad word, but like, data science also encompasses some of these advanced statistics. So we use a lot of Bayesian statistics and things like that to estimate all kinds of things. We are very Bayesian people. We refrain from saying the frequentist yes or no, this or that, A or B. We're very like, it is 80% A, 20% B. There is a probabilistic chance of everything. Because also that's just how the world works. There's never a right answer. There's never one way of anything happening. It's always a combination of ways. So we try to stick true to that.
Fair enough. Yeah. I do have a couple questions before I forget. One, a comment. I'm also a co-mentored, and I know it's awesome. You get like the best of both worlds sometimes. Do you travel to Elon then sometimes, or is it mostly?
No, I'm usually based here. My co-advisor, he which is I think it's great how he does that, because he is a professor with a full-time teaching load, so I think 3 classes. It's a lot of work, yeah. But he manages somehow to keep 1 full day dedicated to research, instead of, people like, oh, I'll have pockets of time where I'll do work, but it's really, really hard to do that. So yeah, since, he's extremely good with his time, he manages to make a trip out here because my advisor and I are here. So we have these hack days, essentially, where we just sit together all day doing science, talking science, and it's really, really productive.
Yeah, both mine are here at UNC, so that logistical challenge barrier just like across it.
Yeah.
I don't have to do any commuting. My second question is rather broad, I guess. So you're looking back in time at a lot of these young galaxies. That's just because of the vast distances light hasn't traveled. I would imagine you know how far away they are, so you can estimate like how much they've grown since. Is that the case that you're looking at galaxies that might be Milky Way size by now, or they're rather close, so they probably have an advantage?
Oh no, they're very close. They're
okay.
in astronomical distances. They're pretty much in your face.
Okay, so you're only looking at the easy, like the close ones.
Yeah, they're close. So I don't know if they're easy, but they're close. They're definitely close. So yeah, I don't think they've had enough time to evolve into such big galaxies. But yeah, they're definitely. So it just gives us, the power to use all these amazing telescopes that we have now, and actually infer a lot of things with them, because for a lot of this information, what's important is the quality of your data, and like quality means resolution, as like how clearly can you see things, whether it's in the spectral rainbow or whether it's in actual images, but also quality in like, I don't, for the lack of a better word, because I've been a scientist for too long, signal to noise.
Right.
Like, how
much static.
Yeah, like how powerful is your signal compared to the baseline noise that there is. And that's just something that you can really, really get with the stuff that's close by compared to what's further out.
I guess this is really dated, but I grew up with an analog TV. And so if you can imagine what it was like, the younger listeners never saw this, but there was a lot of static in the background, right? For some of the, especially some channels. So you would change channels, stuff of what the radio would probably be a better example, right? The car radio, most people have at least listened to once. And sometimes it's really staticky depending on what wavelength you're on. So what you're looking for is those galaxies that are super clear. So you just like change the tune, I guess, by looking at different ones. Do you have like favorite galaxies that you're always looking at, or at this point?
Yeah, I think like it's really great that you brought up that word census, because that's what we call our survey. It's a census of galaxies in a fixed volume of the universe.
Okay. You're just looking at one spot of the sky?
One spot. Well, it is, yes.
It's a big spot.
Yes, it's a huge spot in the sky, or 2 multiple spots in the sky. But yeah, it is a fixed volume, but we don't do case studies. I mean, we do them if they're really, really interesting, but our larger science, or the goal of our research group as a whole, is to actually look at overall statistics and trends, and that is very hard to do if you're looking at individual galaxies, because like what they say, a sample of one is not indicative of anything. So we like to, and that's the thing, and do basically get over the issue of even though they're so close, they're really hard to observe compared to these big galaxies.
Right.
So what we do is we just have to find ingenious ways of spending a lot of time, because the longer you end up exposing your telescope to a particular target, and you just get more signal than noise, because you just end up combining all those observations. And that's how we combat the fact that these are tiny and these are small, and it's hard to do observations with ground-based telescopes, but
So yours are all ground-based. That was another question. Do you have any access to some floating out there that you would love to get your hands on?
We have a lot of we use all kinds of possible archival data from
databases.
from Hubble, from WISE, which was infrared all sky survey. So we have all of that, but the new observations we take, we try to basically get as much out of the fact that we have dedicated time on SOAR, which, like I said, was since UNC was a partner and helped build a part of that telescope, we actually get dedicated nights. So we try to make and it's a beautiful telescope. It's smaller in size than a lot of big telescope, but the optics, the detectors, we have all these holographic diffraction grating, like really, really advanced technology. And I think it competes. So even it's a 4-meter telescope, so it's just a 4-meter big. It's a mirror, so it's a reflective. But yes, yeah, that is 4 meters wide. The DESA primary is, yeah. I mean, there are 10-meter class telescopes, which are, like the most powerful. But even though ours is a smaller telescope, we actually compete with the bigger ones because of the fact that, people through the years from UNC and from other universities have optimized it into such a good state that we have great efficiency and we actually can compete with the bigger telescope. So yeah, so that's why we try to make the best use of the time that we have on it. So we try to do ground-based.
So is it something you visit frequently? I imagine you're not going there physically all that often. You just tell the program where to point it, and then how does that all work, I guess?
Yeah, so it's really cool. I don't know if you've ever been to Chapman Hall. I don't even know if you know where it is, but anyway, it's on campus. There's a remote observing room where we actually have part control of the telescope. So on nights that we get dedicated to look at it, we're on a video conference with the telescope is located in Chile, and it's on one of the best telescope sites that there is in the world, because
on a mountain there.
It is up on a mountain. It's right next to where other telescopes. It's this mountain of telescopes, of amazing telescopes. Awesome. Yeah, so we're on a video conference with the actual operators, the telescope operators over there. So they handle all the mechanical stuff, like actually moving the telescope and moving parts in and out, and we can handle all the other stuff from here. We have a whole room built for it. We have 2 or 3 observers sitting together at night. One person's handling all this stuff to actually it's like settings on a camera. If you've ever used like a DSLR on manual mode, like you have to set the focus and the time, exposure time, and all of that.
I'm gonna be on the microscope after we finish. So
right, yeah, so
you'd know. I know exactly what you're talking.
Yeah,
it's
so
just very different scales. Yeah.
Yes, exactly. They're complete opposite. Yeah. So we're one person doing all that. One person's like in real time, like analyzing the data and seeing how much more we need. So it's a lot of fun. Also, yeah, we have a very easy system that's made easy because apparently a past undergrad built this beautiful GUI for the telescopes, and now we just have to click buttons instead of doing anything on command line. Yes, sorry, I'm sorry about that.
For the non-geeks out there. No, I love it. I take all these things for granted, and I try to lay them out in this podcast. We, people listening from.
That's true.
That sounds awesome. So these are all nighters.
Yeah, it's fun. There's a lot of delirium after 2 in the morning.
Yeah. So are you coming in? Like, have you been awake all night?
Right now?
Yeah.
Oh no. I got my stuff done last week. So nice. Yeah, it's actually kind of interesting because during the day you actually have to do calibration so that you're not losing time in the night, and you actually get a baseline sense of what the telescope, either the noise level or the response and all of that is. So we do that during the day so you don't waste time in the night. And that's done usually in the afternoons. And then after that, whenever it's sunset in Chile, after that, we start taking data if the weather cooperates, all the way until, just a little before sunrise. So yeah, so you essentially have probably at the end of the night been up for 24 hours.
Yeah.
Yeah, it's funny because around the 2 to 3 a.m. there's a lot of like if you're not actually doing work, you're just laughing for no reason because you're so tired and your brain doesn't know what to do with itself. But after that, you're surprisingly extremely fresh because I think your body just doesn't register being tired anymore. It's just like, okay. Like, yeah, so those nights are a little rough because you get home and it's probably close to bright or already bright over here, and then you're like trying to go to sleep, but it just doesn't work. But it's worth it. They're fun nights, the fun experience, and
At least you're doing it with other people.
yes, that is true. I'm like my research group. The way we have made all our arrangements is that we need at least two people to do it. I know a lot of other people who do it alone, and I personally would be miserable. Maybe somebody else likes it, but I like if I had to sit through all night from 7 p.m. to 6 a.m. it would just be terrible.
Yeah, I mean, I've had some late scope nights, but I'm always worried about falling asleep in
Yeah.
the middle of it, so I set alarms just in case.
Or like making a mistake because like when the
Double
telescope
check.
is in the middle of something and sometimes you take a setting to like let it do something for an hour and then there's no way to stop it because if you stop it there's a 50-50 chance of it breaking, well, like the whole system crashing, and then you have to take a half an hour for it to reboot and all of that stuff. So yeah, especially at 2 in the night, I don't trust myself to not make mistakes.
Buddy system.
Yeah.
Yeah, I mean, everything I do in the microscope is like very go, just come in and go out. I don't have that quite that planning. I didn't realize you had to go through all that. One question I had was just a little off topic, and I know you said you don't really center in on galaxies. Are there any that you've seen that are just so beautiful or whatever that are your favorites?
Oh, favorites. Oh.
Favorite galaxies or favorite? Maybe there's a couple merging that you want. I know there's a lot of online resources people can look up and find these things.
Right. I honestly, just because I'm terrible with names for people and galaxies alike, I don't know any names, but I will urge you to even just YouTube searching like simulations of galaxies merging. They obviously show you a fast forwarded view of what happens in millions of years, but they're just so beautiful, and you can see like and again another fun fact, but there are these simulations that people did, and in the simulations I think they stop and show you pictures of real galaxies that are doing exactly that, and it's crazy that simulations completely independent of observations reproduce almost exactly the same thing that some other galaxy that somebody else observed, which is really really cool. But yeah, unfortunately I don't
Okay, I was just wondering.
remember.
I don't have like any favorite cells or anything. Some people, yeah, like get very attached and
Right.
So you do these all-nighters, these 24 hours. I know you're probably don't have a ton of free time, but I always like to get to know.
Right.
So other hobbies, they don't have to be science related. But they are.
Okay, first I will say that we do these all-nighters and these extra long days and these telescope nights. However, my usual days are spent all day sitting and coding on Python in front of my computer. We contrary to popular belief, everyone's like, "Oh, you're an astronomer. You must be like out looking at the night sky all the time." I was like, "No, I wish I did, but this would be a luxury for me if I actually could, be out somewhere looking at the night sky." But no, I don't get to do that. Like any other grad student of any other program, anybody who does data analysis, that's my day to day. It's very not very glamorous. I'm in an office on my computer, staring at the same piece of code for hours together, trying to figure out why it isn't working. Yeah. And then you realize it's the dumbest thing. It's either a version change or a semicolon or something stupid like that. Anyway, Yes. Yeah. Anyway, complete aside, but yeah, hobbies. Well, like to do a little bit of everything, but one of my favorite things to do, and apart from work, this is what gives me motivation to, you know, uh, reach my goals because I love to travel. And yeah, I think my whole life is a series of I plan everything around my next vacation. So it's like I have time now. I'm gonna go for a vacation here. Before that, I need to finish XYZ goals. And
You're satisfied when you go
yes,
on
so
it
I'm
instead of feeling
satisfied.
guilty.
So my advisor is satisfied, so that I feel
Yeah.
like I'm not cheating my time in grad school, and but yeah, travel is extremely important. I love to take pictures. Some people get annoyed with me when I'm traveling, but yeah, I it's funny because I only got my DSLR like not very long ago, but now it's almost like I've forgotten how to travel without it. Like I just like if I'm without my camera, I feel very naked and vulnerable. I'm like I don't know how I'm supposed to enjoy this, but yeah, love taking photos. Uh, and that's one of the main things. But on a day to day, I cook a lot. So love cooking, love experimenting with food, or just uh, one of my favorite things is Indian food is, I think, very largely underrepresented because Indian food, like in India, like every 100 miles or so, the language or dialect changes, the food changes, people's habits, just like cultural changes are there like every 100 to 200 miles or so. So there's so much variety of food that is just not reflected in what you see in restaurants. And I'm vegetarian, and even I have so many different options. Like I've never felt like I've run out of options just because I'm vegetarian, and I think that's largely because just there's so much variety of Indian food that people are not aware of. And that is one of, I think, I would say my hobbies is just to uh, make different kinds of Indian food and feed people and be like, hey, look at this, isn't this delicious? So yeah, and if I'm feeling alive and energetic, I love to karaoke. Yeah. So always down for karaoke.
Yeah, you gotta make time for stuff like that.
I agree.
Keep yourself balanced. Burnout and very useful.
That is true. That is very true.
You don't stargaze when you travel? You
Uh
kind of alluded to that.
I do I do and I don't. It depends on, obviously where, when. But yeah, I mean as much as I can. Again, the thing back to photography, because taking pictures of the night sky is amazing and fun, but it's also technically a little bit of a challenge if you're new to it, like I am. So that's always the challenge for me is I've been on nights where it was like extremely windy with like sand in my face the whole time just because of the weather in any of these national parks. But the challenge is to be able to get that really nice shot. So yeah, so and while that's going, if there's somebody with me, I know to read part of the night sky, like in terms of constellations and stuff. So um I if someone's with me who doesn't, then I share my knowledge. And with the constellations, you're pointing out to different stars or nebulae or something like that, and then they get a little bit tidbit of science of
Mini
what
lecture,
those things
maybe.
are. Yeah.
I'm sure they appreciate it. 'Cause
I hope
space
so.
is, I mean, it's fascinating to me. I've been watching The Expanse lately. I don't know.
I have no.
Yeah, I don't know how true to form it is, but it's be fairly accurate. Maybe we should. Is there anything in Interstellar, if you saw it, that had an issue with as an astrophysicist? Any
Oh
myths
God,
or
this
any
is
other
gonna be
myths that
controversial.
you wanna bust?
Um, Interstellar. It was a really great movie, and very, very few movies I walk away from it and days later, my mind is still bent. Interstellar was one of them. And I think what I liked was the explanation of so many things, like whether it was a wormhole or whatever. Like, it was 30 seconds they took in the movie to explain, and it made an impact. And the amazing thing was that visualization of a black hole was incredible. Like, I had never seen anything like it, and I was like, this is almost scientifically accurate. Like, this it's amazing to see like movie makers take the effort to actually scientifically reproduce something. So that was great. My issues, oh Lord.
You don't have to have any.
No, I mean, okay, so the thing is, like, my biggest complaint about that entire movie was the ending. I was just so disappointed. And I know everyone, thinks I'm crazy. They were like, of course, love conquers all dimensions. It's like, yes, I get it. But you don't fall into a black hole and wake up behind a bookshelf. This makes zero sense to me. And I know that they're allowed some creative license. Yeah. But, and obviously, like, nobody knows what happens after you fall into a black hole. Like,
but probably not end up behind
not end up behind a bookshelf. Like, I have no idea. And yeah, I like, that thing completely threw me off. I'm like, there should have been a better way to end this. But I still love the movie, don't get me wrong, but it's just that it's like, behind an event horizon is a bookshelf. What? I was that, I think, was just like, no, as a scientist, I will not digest this. Yeah. And a lot of other scientists have been like, you're crazy for not liking the ending of the movie. But I'm just like, well, okay.
How would you have ended it?
Oh Lord, I don't know. I don't think I have a good answer to it.
It doesn't have to be scientific. Or like, what do you think, in your opinion, this is away from the science, what do you think happens? Fall into a black hole?
Just think, like, just because, as I was saying, that the gravity there is so extreme that you're bending space-time, and you're just it's like this down to infinity kind of situation. And I know infinity is a very abstract concept, but I just feel like you would just feel like you were falling till the end of time if you even made it there in one piece. Right. Like, also from what I have gathered about black holes and things that happen around them, like, if you were close enough to a black hole, like, if you remember that the visual, there was like this like ring of light and everything, and that's what we call the accretion disk. So that is when a black hole is actively heating up material, and it's just because, like, all the dust and the gas and everything around it, but things don't just fall into a black hole. It's similar to, like, when water in a sink or a wash basin, it will swirl around and then go in. The same kind of thing happens with a black hole, that things just assimilate in this kind of a disk structure around it, and then will slowly circle and fall into the black hole eventually. So and the reason that they glow is just because of the extreme the gravity over there, that they just become hot. They actually are radiating a very, very large amount of energy, and they like actually start glowing hot almost. So that's why they are accreting, and that's the kind of black holes that we actually are able to detect, because then you actually see this accretion ring around them, and you're like, okay, there's this black hole that's doing things. So so according to my knowledge, I think if you went that close to a black hole, you would just sublimate into essentially space dust, and there wouldn't be a you anymore. And if somehow you manage to cross that event horizon, I just think you'd be falling till the end of time, because the gravity is so strong. I feel like time would move like extremely, extremely slowly for you. So you would just be like falling and falling and falling until the end of time.
Until it all ends,
which
fair enough.
may not be such an exciting ending,
but I can understand why they ended it the way they did.
Of course.
Just a little less glamorous. But yeah, I'm always curious stuff I know nothing about. I'm very. Are there any other like myths in the field of black holes that you spell, things that you hear online or wherever that you're like, it may not be the case. I don't know.
Yeah, I think the biggest one is what what I alluded to earlier, that people and I didn't even realize that this is the reputation of black holes, that they just go around chomping everything in sight. But from the past discussions that I've had when I was doing outreach with people, is they were just extremely disappointed to know that was not true. And I was like, I'm
a little
sorry.
less exciting.
Yeah, they're like, oh no, like there were these cool very lethal creatures. I was like, yes, they're very lethal. Still, I would not suggest approaching a black hole, but they just don't like do anything unprovoked, I guess.
Gentle sleeping giant.
Yeah, I think like all other animals in the wild, right? Like nobody actually does anything unless you provoke them. Yeah.
They're rabid, yeah. Generally, they're more scared of you.
Yeah.
So how did you get into this field? You said you had done this previously. What drew you to this, other than the immense gravity, of course?
Oh, unintended. I hope. Yes. Yeah. So, I don't know. I was a very curious child, and I know this sounds like this corny story, but I think my parents would add annoyingly curious, but I was just always had 5,000 questions. And my dad is a very scientific man, but loves like Indian mythology and astrology and all of that, but in the context of of actually being like astronomical. Because when you think about it, I'm not sure how much you know about Indian astrology, but even our zodiacs and stuff are very different. And they all, we follow a lunar calendar, but like all of the zodiacs and everything, and the zodiac sign you're assigned at birth is not fixed like the Gregorian calendar with the time of the year. It's more of when you were born, where was the moon. So there's a lot of actually like astronomical calculations going on of placing stars and constellations and moon and in the moon and all of that. So it's very interesting in that sense. Of course, like all mythology and astrology, there are questionable aspects to it, but yeah, it's very interesting in the way they even figured out there's a lot of like calculation and actual precise math involved just to assign you a zodiac sign, which to me is incredible. So he was always interested in that, and would always talk to me about stuff like that. And my dad actually worked on shore in a natural gas plant. I grew up in Dubai, for context, so or Abu Dhabi rather, but he worked in a natural gas plant, so he would come home only on the weekends. So every night, though, he would call me and, tell me a story, and whether it was about mythology or astrology or whatever, it was just, stories. So that's how I got interested. And then I started asking too many questions, and they got fed up with me, and they just dumped a whole bunch of books in front of me. They're like, okay, here are the answers to your questions, because I don't know.
Awesome.
Yeah, and that's how I think the interest grew. And I don't know, at some point, when you're a kid, people always ask you, what do you want to do when you grow up? And my answer initially, because I didn't know better, was I wanted to be an astronaut, because I didn't know that there was a difference between an astronaut and astronomer and all of those things. I just thought that space was space. And later when I realized that, astronauts involve going into space, and I'm like, I don't know about that, but I want to be an astronomer, and I want to learn about space. Yeah, and I think, like, and as far as I can remember, that's what I've always answered people. And I don't know at what point it was just, like, I think as a kid, everyone's like, oh, I want to be an astronaut, I want to be a pilot, I want to, be, I don't know, an alien. Like, there are a lot of kids like, I want to be an alien. I'm like, okay.
Good luck, yeah.
I'm like, you technically, like, if you went to Mars, you would be an alien, right? Like,
you go to another country and be an alien.
that is true. Yeah, my current immigration status is non-resident alien. So yes, I have achieved it. Become an alien. Yeah. So I don't know at what point that fantasy as a kid just cemented itself as okay, this is what I want to do. But I remember when it was time to go to undergrad, I was like, okay, no, this is what I want to do. Except that I was 15 at the time, and my parents are like, well, we're not letting you go to the US or UK to study because you're too young. And the thing is, in the UAE where I grew up, or in India where my origins are from, so there wasn't really a good infrastructure for that. And it's funny because over here I don't think there's a difference, but in India a Bachelor of Science degree has a lot less value than a Bachelor of Engineering degree. I don't know why that is, but that is true. And my parents were worried. They're like, what are you going to do with a Bachelor of Science in Physics, and I understand their concerns. So we made a deal after a lot of talking that they're like, okay, do engineering for undergrad, and then after that you're free to do whatever you want. You can do absolutely whatever you want. So I did some research and I ended up doing a Bachelor of Engineering in Electronics and Communication Engineering. So and that was my informed choice, because that's when I realized that a lot of this involves data analysis and signal processing and image processing, and I'm like, this makes sense. This is probably the field that I should study at. And I actually am very happy that that's what ended up being my path. I think the engineering training gave me a lot of skills and just, I think, drilled a lot of intuition about things that, about whether it's like coding or building algorithms or how to deal with data, that I'm glad that I got. And then I moved on to a master's in astronomy at the University of Florida. And I was at a conference and presenting my research, and I met my current advisor there. And we realized that we had similar interests in the actual astrophysical science, but also in terms of method. Like, we both wanted to use advanced statistics and stuff like that. So then I applied to UNC for my PhD, and I'm here now doing this work. So yeah, that was my journey.
Oh, it was really well defined. Some people have different paths they come in. Seems like from a very early age you had been inspired enough
and that was my whole master's. Like, for me, it was one, I was excited about it, but then I was also like, I think until then my goal was just like, I need to get accepted into a program. I need to, this is what I want to do. Except that while I was on that 16-hour flight here, I was like, what am I doing? I have never had any formal training in physics or astronomy or anything like that, and I'm going to this new country to do this. And I was like, what is wrong with me? And that's when the doubt kicked in, where it's like, is this just like a childhood fantasy that I didn't actually correct? I didn't actually rethink my childhood fantasies. But then I came here and took classes, started doing research, and I was like, I don't know why I've been doing anything else my whole life. This is what I love. So it worked out for me. But word of caution to people is just don't always assume that your childhood fantasy is what you want to do. Always have a backup. And I'm glad my engineering degree gave me that. It's also good to know. It helped me be a little more brave, knowing that if this didn't work out, I had something to fall back on. So I think that was a smart decision my parents made for me. But
as they often do.
Yeah.
Lived the life before you.
That's true. Yeah.
I really appreciate it, Mugdha. This has been great. Anything else for the audience? Things you wish people knew? It could be away from black holes and dwarf galaxies. Right on.
I would just say that a lot of people have this stigma towards math or physics or science is hard, and it is hard. But what else is hard? Like life, everything is hard. I don't think any grad student or researcher or somebody who, you know, he was even a working employee will tell you that anything is easy, because it isn't. So if you truly have an interest towards something, just don't let the fact that you are scared of math, or, you know, be like, I don't like math and I will never pursue a physics career. Because yes, it's important, but what's more important is your ability to think through a problem, to solve a problem, to you know, when you hit a brick wall, it's what you do next, rather than how you do it is what's important. So yeah, so don't let, you know, the stigma of, you know, people telling you that math and science is hard stop you from you know, being a researcher in any of the hard sciences, for that matter. So
Yeah, I'd say that too. Although math was very scary for me.
I'm not saying that it's not. I'm just saying that, you know, that should not be the reason that that people don't even try. Like, I guess if you try and you don't like it, that's one thing. But I have seen a lot of people who won't even try taking a calc class before they decide whether they want to be a physics major or not. And I'm like, that it's heartbreaking, because, you know, you see the interest, you see the potential, and as a, you know, as someone who's been through it, and I was like, no, I'm 100% sure you can do it.
It just has a bad reputation.
Yeah, it's hard to fight a reputation, but I think at some point we just need to rip the back off and just go for it.
Again, Mugdha, thank you so much.
No, thank you for having me.
Thanks for listening all.